Hello everyone. Can you guys hear me? Hello.
Yes.
Okay.
Yes, ma'am.
Yeah. Hello everyone. Welcome to our January MMMRN seminar. This time we are very delighted to have Dr. Abdullah Al Amin Bhai, who is a very long time friend and beloved founding member of MMMRN. So before we start, I want to share a brief bio of the speaker. So Dr. Abdullah Amin Bhai is a postdoctoral scholar at Mechanical Engineering Department at Northwestern University. He received his Bachelor of Science on 2009 from Bangladesh University of Engineering and Technology, a Master of Science from the University of Akron, and a Doctor of Philosophy from Case Western University, all in mechanical engineering. He has 3 years of industrial research experience with Bridgestone America Technical Center in Akron, Ohio. Dr. Amin's research focuses on laser power bed fusion additive manufacturing process to improve the manufacturing of complex engineering parts. He utilizes high-performance computational resources, multi-CPU, GPU involving multiscale and multiphysics analysis of FEM and CFD methods to analyze and design large-scale engineering systems. His research also involved the design of microelectromechanical systems, MEMS, automotive tires, and biomedical systems. He co-invented a biocrystal detection system with laser light and a refrigerator magnets suspended in biofluids. Among his notable recognitions is winning 4 awards in the 2022 NIST Additive Manufacturing Benchmark Channel Series. So I welcome Dr. Amin to start his presentation. Thank you.
Thank you, Pritham, for nice and a flattering introduction. I'm not sure whether I am worthy of all of these praises, but thank you anyways. And just to get started and check everything, I'm guessing everyone can hear and see me clearly at your end. And if there are any issues, just let me know. We'll try to figure this out. So without further speaking, I'd like to jump straight into my presentations today. As you already know by the title that I am going to talk about designing 2 large-scale systems. One is MRI magnet design, and the second is the additive manufacturing process. So jumping onto my next slide. Okay, so before we get started, I'd like to provide an overview of what is coming up next. So if you find it uninteresting or let's say very dull, then you can leave any time and come back at a later time when you think it is more appropriate and more interesting for you. So as you already know that I have worked on a couple of projects, I'm going to talk briefly about some of the key projects that I have worked in the past. I'm just going to summarize them. And later on the second phase, I am going to talk briefly about the additive manufacturing, the techniques and technologies that I have used and what are the results, what they mean, and also the design of MRI magnet. This one was my PhD research projects. And if time permits, depending on how we progress and if there's interest, I will spend a little bit of time explaining what did I do as a tire research engineer. And we have about 15 minutes of questions, answers, and discussion. So we can switch from formal discussion to informal. If there are any questions outside the presentations, I'm happy to take it and then follow through with the discussion. So that totals up with 60 minutes of our time. So let's get started. So the first project, the brief project that I worked on after coming to US, I was a fresh graduate of BUET back in 2010, and then I started working at University of Akron. The first project that I worked on was a MEMS device. So with a 2D sketch, this is what it looks like. We have electrodes, the red and the golden color respectively shows the positive and the negative polarity. And we have an insulating Teflon layer with designated with this blue solid rectangle, and we also have an ionic liquid with this yellow geometric shape. And the objective is to pick up some micro objects which are very small, very delicate to handle. So in order to handle those delicate objects, we are relying on the surface tension. And in reality, in a microscopic image, this is what the liquid looks like. The black actually is representing that no light is passing through. That's why it is appearing black in the microscopic image. But if you compare these two images side by side, you would be able to see that the contact angle has a difference. So the first one has a contact angle of about 90 degree. The second one has a contact angle of 65 degree, which is much less. But if the contact angle changes upon the application of the electric voltage, we do have a change in the force that it can be used on picking up micro objects. So this geometry is actually flipped on this image. So this ionic liquid is actually on the opposite direction, as you can see. And this is the setup. The device is actually attached on the end, at the end of a lever, and we are applying voltage through some electrical wire. And if I go down to the micro scale, trying to look at the red and golden interdigitated electrodes, as you can see over here in the microscopic image, in reality, it does look like that. So when we are applying the electrical voltage, it does try to change its contact angle and then gets to a steady state, beyond which if we try to increase the applied electric voltage, it will then break down. And we can use these setup to pick up micro objects for different, the different distance, and also the amount of suspended liquid that we can estimate from this particular image. So this plot actually demonstrates that we can pick up objects of different weight and then change our manipulation based on our needs. So that's the first one. There was no computational analysis involved. But on the second one, that was my master's project. So I designed actually a microfluidic separation device, which from this CAD geometry or 3D render, you can see that they have different width as I move from the center to the outer side. So this picture on to the left actually is the original manufactured image. That's what it looks like. And the underlying mechanism behind is that the force balance. When a microchannel is carved, there are additional forces, which we call the Dean force, as specified by the purple FD, as you can see. And in addition to that, there are other forces like the self-weight of the microparticle, the wall shear that is coming from particle being near the wall, and also a shear force, which is represented with a yellow arrow, and also the buoyancy force that is acting upward. So if I implement that into ANSYS Fluent, which is using finite volume method, from the inlet as I move on to the outlet, as you can see, the numberings are 1, 2, 3, and progressively going towards to the outlet. And at the top is the experimental image recorded through a microscope, and the microparticles of two different size, 10 micron, represented by the blue spheres over here, and also the green spheres are the large microparticles, and the blue spheres are the small microparticles. Those are of 5 micron. So at the inlet, they were uniformly dispersed, and as it progresses towards the outlet, there is a clear separation between those two. So this is what we can observe in experiment. And if we try to model that in some form of, let's say, commercial software packages as in ANSYS, we are able to see the simulation results. So this is kind of my first venture into comparing the experiment versus the computation, and then understand better. And I realized that if I do simulation, then it can tell us or give us more information that would be otherwise expensive or difficult to get from the experiment. So the next one, as you probably heard from the introduction, that I conceived an idea when I was working during my PhD with my mentors and also other collaborators. So this was basically trying to detect some biocrystals out of some biofluid samples. So this is the mechanical system that I have designed in a CAD program that was Creo, if you heard about it. And this is the underlying mechanisms. So we are applying some magnetic field using the magnet, and those magnets are actually attached to these blue solids. As you can see that the magnets are pointed with a red arrow going to the left and to the right. So that means there are different arrangements of the magnets, and we have a sample inside this cuvette, which is basically a sample holder. And we also have a laser light that is passing through a polarizer and through a beam splitter so that we can detect the intensity of the signal using a photodiode before passing through the sample. And also after passing through the sample, we are also again recording it using a second set of photodiode and using a general op-amp circuit. If you have taken your instrumentation course or let's say op-amp course or electronic course, you can design a simple circuit to detect their difference. And what happens is if we apply a certain direction of the magnetic orientation, those biocrystals can be oriented based on the magnetic field. And based on that, their change in intensity can be recorded. And we should be able to see the difference in the electrical signal. And based on the intensity of the signal, we can also estimate the concentration to some extent and then identify the biocrystals suspended in the biofluids. And one particular example of this method is to detect gout crystals. If you know about it, it's actually accumulated near the knee or the ankle of a human, and sometimes it can be really, really painful. And in order to detect those, before you get any medication, you need to detect those. And the conventional technique is really time consuming. You need to draw some sample with a needle and then send it out to the lab, and then under the microscope, they will identify and detect those biocrystals, and the results usually comes back in about a couple of days. And by this time, the patient is suffering this like unbearable pain. But if this device is made to work, it can be a standalone system where you can place your sample and then get the results in a matter of 5 minutes. So that was the idea, and there was a patent that was granted, and this was a work that I have done as part of my PhD research at Case Western Reserve University. So this is the original topic of discussion. This is the first one, the additive manufacturing. And the process that I would be talking about or modeling is the laser powder bed fusion. And if you know about additive manufacturing, it is a little bit different than the conventional subtractive manufacturing, where you try to machine out the material out of a piece of a block to get a desired shape of the part. But the additive manufacturing is a little bit different. And what I want to do is play this video from 42 minutes mark. Let's see if it works. Okay, looks like we have our first hiccup. Let me see. I will jump right over here. So what you can see in this, okay. What you can see in this video is that there are some metal that is being welded. So there is a laser that is not visible, but it is actually hitting a metal surface, actually a layer of powder. As you can see, there are some inert gas in the atmosphere, and this kind of blue thing, so those are actually the metal powders. And the particle sizes are basically 5 micron all the way to 100 micron. So they does vary. And these, as you can see, the laser light is now focusing and then pointing towards a specific direction and then trying to weld those powder all together. And that's what you were seeing. And this powder coater is basically moving through layer by layer and then spreading a next layer of the powder. And the laser is melting certain amount of materials to fuse and then generate a specific microstructure. It can be some larger structures too. And just to give you some examples, additive manufacturing nowadays is being used to manufacture some aerospace products and also parts and also rocketry. If you heard about what's that called, the relativity space, if you Google that name and then go to their website and also land onto some of their YouTube videos, you'd be able to see that they're actually manufacturing a rocket by additive manufacturing. And they are using a similar technique, but not completely this same technique, and that is called the directed energy deposition method. And this one is a laser powder bed fusion method. But from the video, you can see that it is possible to manufacture a very complex part within a very short period of time. And if you were to machine it using a lathe machine or some other form of, let's say, other form of conventional machining process, that would be difficult or time consuming, and also the quality would not be maintained. Okay, so this is in short the overview of what an additive manufacturing laser powder bed fusion looks like. So let's get to the next slide. Sorry about that. Yeah, so this particular sets of equation, you probably heard about it. You already studied a lot than I have done. But the first one is the continuity equation. So these are basics that are taught in the class in fluid mechanics. So I'm not going to spend too much about it. The second part is a momentum equation. And this is what this equation basically is doing, is creating a balance of the forces. As you have learned from your high school physics, is that the forces needs to be in equilibrium for any systems when you are trying to solve an engineering problem. So this momentum equation is trying to do exactly that. And if I try to explain it a little more, this rho here is kind of a density, and that relates to the mass of a system. And the velocity that is changing with respect to time, that would be acceleration, right? So the acceleration times the mass, what we get is the force from the Newton's second law, right? And this is a convective term, meaning like you are already familiar with convection, I'm assuming. Convection means that some of the molecules or maybe materials are being transferred to in terms of convective heat transfer, I think it might be easier for you to pick up, like it's actually convecting heat from one place to the other. And that also plays a role into the momentum equation. And this equation is telling you that all of this is equal to the change in the pressure gradient. And because of that change in pressure gradient, there is a force arising. We are considering that force and adding them with the diffusion term. Diffusion is when the particles are actually diffusing, and also the gravity force. In addition, there are some buoyancy force if we are considering, and there might be some other additional forces. For example, what I'm trying to model over here to accurately describe the additive manufacturing is Marchian resistance that comes as an additional force term into this momentum equation. And in addition, there's this energy equation where I'm trying to solve the enthalpy of the system and then relating it to the temperature change, as this is a process where the materials changes their phase, like from liquid to solid or vice versa, from solid to liquid. And there is a change in temperature that I can record. And usually in reality, temperature is the one that we can measure. It is very difficult to directly measure the enthalpy with the instruments that we have. So all of these equations in combination is called the Navier-Stokes equation. If you have not realized by this time, that is what it is called. Two gentlemen back in 18th century, they independently derived this form of equation. And here we are, about after 250 years, we're still trying to solve it. And in most cases, we solve it numerically. And if you are interested, you can go to this page and then study more about it and then understand. Is there any question?
I think someone, yeah.
Okay, so I will continue. So yeah, on the next slide, the additive manufacturing process that I have described in the previous video, if we look at the micro scale, so this is what it would look like. It is actually an X-ray image of the process. And when we try to record those changes, as you can see, the laser was moving from left to the right. I will try to play it again for your benefits. As you can see, there are some change in color, and those change in color are actually defining two different phases. As you may understand that the bright spot are basically some form of, let's say, voids through which laser can easily pass, and that's why there is no, that's why they're bright, and through which the, sorry, I mentioned laser, that should be X-ray. So we are actually taking an X-ray images, and through which the X-ray cannot pass, those are basically darker. And there are an instrument that can also record the absorption, like the amount of light that is coming back, and the laser is coming from the top and then being reflected on the surface and then going back. And the amount of laser that is going back, we can record them in a sensor. And if we try to record them, we will see that there is a fluctuation or change. And in mechanical terms, or let's say people who are associated with additive manufacturing, particularly laser powder bed fusion, they are called the absorption, meaning the amount of energy that is being absorbed into the system. We can estimate that by recording the amount of energy that is being reflected. So in other words, this is maintaining the energy balance. The amount of energy that is going from the laser into the system is estimated from the amount that is escaping out of the system. So that's what the absorption curve is. But this is important to understand the additive manufacturing process. And in the 2022 NIST experiment, they had different scenarios, like for which they actually run single track simulation. And also by single track, I mean, this is just one pass of the laser. So that is single track, but it can actually come and come back, and it can go and come back. So it's like multiple lines of scans side by side. So NIST is National Institutes for Standards and Technology. It's in United States, and their objective is to study and standardize different methods and techniques. So one of their division is trying to standardize some of the additive manufacturing process, trying to understand it. So they have different types of measurements, and they have done it experimentally. They're pretty good at it, and they are very confident about what they do. And they invited all the modelers across the world, not only within the US. Anyone from any place of the earth can submit their computational predictions. So that's what they did. That's what they announced at the beginning of 2022, sometime in January and again in April. And then they invited the modelers to submit the predictions. So since I am a mechanical engineer, I know a little bit about Navier-Stokes equation. I did write my own C++ code, and then I solved this particular problem and tried to predict some of the measurements that they have done. So this animation onto the right, let's explain by playing it again. So what is happening is the laser light is moving from left to the right. The top one is a solid phase, like some of the phases that are being melted. The center one is the temperature, and the bottom one is the isocontour, meaning they are actually at the melting point of that particular metal. So I can plot the temperature with respect to time, and I can also study the length of the melt pool as the time progresses. On to the next slide, you can see similar animation, but I can also keep track of how this length is varying as the time progresses. after some time, we can see that the length does not vary that much. And that is the location where we want to make our measurements. And we are particularly making a measurements around this region. That's what I'm going to play next on this animation. So what we are going to do is make some measurements during the steady state, as you can see, and I'm actually zooming in around this particular region. And this clearly shows that there is a discontinuity in the function or in the graph that I am plotting. So if I draw a slope going upwards in the temperature, that means this is the liquid phase. And if I estimate the slope, that would be the slope of the melting and actually the rate of melting, like how fast it is melting. And the, let's say, engineering terminology is the melting rate or the solidification rate. Solidification rate before the, let's say, material is entirely being solidified. So in the NIST term, they call it the liquid cooling rate, that like the liquid is being cooled to the solid region. And the black tangent that you see, this slope tells us the solid cooling rate, like after the entire material is being solidified, how fast or how slow it is being cooled down. And these are some of the important studies, and then gives a very detailed idea of how the process is going on for the additive manufacturing. So now back to this table, there are about 7 different process conditions for the NIST test that they have done. As you can see, they have coded it with some case numbers, and the laser powers, they've actually tried many different laser powers. It's actually 3 in this particular case. They also tried varying the scan speed and also the spot size. So NIST came out with this clever idea that the amount of energy that is going into the system is basically dependent on all of these 3 parameters. And NIST gave them a name which is called the volumetric energy density, in short, VED. And we can calculate the VED for all of the respective cases. And if I try to plot the similar graph that I have shown before with respect to the time, the change in temperature for all of these 7 different process conditions, we would be able to see that their characteristics are different, meaning like the time when the temperature goes up and comes down is different. And this tells us that if I change the process condition, some of the characteristics behavior of the additive manufacturing changes, and then we can get useful information out of it. And this also allowed us to make some measurements numerically on our simulation. For example, on this plot, it's actually, these plots are actually a pair, like the picture on this left bar chart and also to the right, the scatter plot. They're actually the same plot, but plotted differently. So there are about 1, 2, 3, and 4 different sets of graphs. So let's discuss them one by one. The first one is I'm trying to make the measurements of the melt pool depth. And it's actually, the depth is estimated from the top surface of the additively manufactured powder bed down to the level where it has the, let's say, maximum melted region. So you can think of it as a penetration of the melted region. So for different process conditions, these 7 case numbers, so the blue bars are actually representing the experiment. The red one is the first type of simulation that I have done. This is using a heuristic calibration. I'm not going into too much detail about it, what the heuristic calibration is, but this is actually a method to approximate the amount of energy that is going into the system to model the additive manufacturing process. So the second one is similar to the first heuristic calibration, but it is relying mostly on the data. So I am trying to analyze some of the literature data to come out with a more uniform, more accurate heat source model so that we can have a better prediction of the melt pool depth. And that's what I'm plotting over there and trying to compare. And it looks like the experiment and the computational prediction does have a good agreement for both of those methods. In addition, not only looking at this bar plot, I tried to plot them against the volumetric energy density and then wanted to see if there is a correlation or any hidden physics that we can reveal. And what you can see, or I can understand, that this is mostly linear, meaning if I increase the amount of volumetric energy that is going into the system, my melted region would have greater penetration depth. So that means it is a useful information that I can leverage and then manufacture more meaningful, or let's say more quality product. So that's one thing. And also this is the melt pool width, meaning the wide, like how wide the melted region is. Again, I try to compare them with two different alternative techniques that I have implemented. And I also tried to plot them against the volumetric energy density. And as you can see, the red one does have some discrepancy at higher volumetric energy density, meaning there are higher errors. But if I improve my heat source approximation technique, it also improves the prediction capability. And in addition to that, the other two measurements that NIST asked the modelers to submit at the time above melting, meaning how long a particular scan track has been on the liquid region. So that's the time above melting, and then I try to compare them with the two different methods. Again, in a similar fashion, I try to compare them with the volumetric energy density and then see if there is a linear or nonlinear or a mathematical relation that I can come out with. In a similar fashion, the solid cooling rate, as I can see, the red method is giving us some error, but that improves or kind of mitigates the deficiencies if I use the novel techniques that I introduced. In a similar fashion, if there are multi-track, like not only one line of scan, so this is basically a cross-section. And if you think of it, the laser scan directions are actually coming out of the plane. So it's coming from behind and then coming out of the plane and then going back from the front to the back of the screen. And there are multiple tracks. So whether we can model them and also identify or estimate the depth and also the width of those particular scans. So with our computational code, which is relying on finite volume method, yes, it can. And as you can see, it does compare pretty well. And in addition to the depth and width measurements, there were also some measurements involving the depth overlap, meaning like from the top surface and at the bottom, when those two characteristics, melt pool geometries, are being overlapped, what is their depth? So that is the depth overlap. So I'm actually estimating the depth at position here, there, and so on. And also for the width, there is a term called width overlap, meaning if you were to draw an imaginary line that is going up over here, and also this particular melt pool that is ending over there. So what is the distance between this one and the other imaginary one? And when I make those measurements, they do also have some good agreement between them. So this was the additive manufacturing simulation for powder bed process, and that was using finite volume. And now we are switching our focus a little bit towards to the finite element method, which is let's say different technique than finite volume. And in this particular case, I'm trying to show how we can leverage the finite element method to design the MRI magnet design. So if you have not heard about superconductivity, the superconductivity is a particular phenomenon when it can carry electricity without any resistance. And that was discovered in 1911 by this physicist. And there was a Nobel Prize awarded in 1913. And from this plot, as you can see, for this particular black dot or black scattered plot, it was having some resistivity, and then suddenly there is a huge drop in the resistivity, and that's what it is called the superconductivity, meaning the resistance of material goes too low. And in terms of physics, if you are more into understand or trying to understand the physics, is that the flux lines usually try to avoid that particular zone. And that's why there is no resistance. So it has applications in many different engineering systems like MRI, it's for biomedical imaging. If you heard about maglev train, that's where it has some applications, and also superconducting motors that are mostly used in, let's say, wind turbines in some cases. So what I'm trying to do is trying to understand and trying to give you some background of what MRI machine is about and where the challenges are coming from. So when I was doing my PhD, there was a crisis in the price of liquid helium. The prices were going up, and the amount of liquid helium that we have in this Earth is also limited. And in MRI, the liquid heliums are used in a very large quantity. And in those cases, you cannot manufacture infinite number of MRI machines because you would run out of liquid helium. So engineers and scientists were looking at different alternatives, and magnesium diboride is one alternative which has higher critical temperature, meaning it starts to be superconductive at a temperature much higher than other conventional superconductors. So just to give you a reference, magnesium diboride superconducts at a temperature below 39 Kelvin, whereas the conventional niobium Ti superconducts at a temperature below 9 Kelvin, which is much smaller. So why this is beneficial is if you have a critical temperature greater or larger than the conventional superconductors, you can look at other alternative cooling systems rather than a convective cooling system, like submerging all of those magnets into liquid helium. You can use some form of conductive cooling. And this particular plot was showing some simulation. It's actually a Monte Carlo simulation showing if the helium crisis was going up, then the demand would go up to a certain point and the new technologies would arrive, and then the crisis would fall down. So as a scientist or engineer, our goal or objective is to bring this time much earlier. So can we bring it closer to 2025 rather than 2031? So that's what this plot was showing. And this picture was showing a basic construction of the inside of an MRI. It has background magnet, which in other terms called the main magnet. And that is where my focus is. And this is the intermetallic structure or the atomic structure of magnesium diboride. And during my PhD, using this magnesium diboride, I was trying to design a conductively cooled MRI magnet that would not use any liquid helium. So that was the objective. And now you know the reason why I wanted to do it. So in order to model the MRI magnet, you will have to go through actually four different processes. The first one is actually manufacturing the magnet. Second one is cooling it down from room temperature down to a cryogenic temperature. In my case, it was 10 Kelvin. We have about 29 kelvins of factor of safety. And the next step is you can electromagnetically excite it. So when you pass through a large amount of current, it will generate a magnetic field. And because of that magnetic field, you can align some of the protons in your body and then send radio signals and then receive those radio signals and then reconstruct the images for those tissue. And that is one of the most preferred imaging techniques in biomedical systems, if you do not know, because this is the only one that does not have any radiation effect. But for the other non-invasive imaging techniques, like if you talk about X-rays or CT scans, there is a certain limit. You cannot have X-rays every now and then. You will have some form of biological anomaly into your system, but MRI does not have those. So again, coming back to the final stage or final process, this is the quench process. So it's not like you design a thing and everything goes smoothly. There are occasions or events when there are some small disturbance. Because of that, some part of the magnet become resistive and then they generate huge amount of heat. And if you do not take any preventive measure, your entire magnet would melt. And an MRI machine is usually cost around several $1 million, and you do not want to happen that to your MRI machine. So on this next slide, what I'm showing is a construction. So this is at the large scale. That's what we can see. If we take a very small, tiny rectangle cross section out of it, we have this one. And on that cross section, you will have many, let's say, cells of the wire, because you are actually winding the wire around a structure. And it will also have many layers. Like if I count from right to the left, those are actually going across the layer. And if I consider a small, tiny rectangle, as you can see over here, at the microscopic level, they are composite. And when we are computationally modeling it, I will need to get its property. Like I can do some form, let's say, finite element to use that to computationally estimate what would be their properties, because I would need to solve some of these driving equations. So similar to Navier-Stokes, Maxwell is another sets of equation that actually connects the magnetism, electricity, current going through, and also eventually the forces that is arising from it. And you also need to solve the Fourier heat conduction equation, because I was working on the conduction of the conduction cooling of the system. And also this is actually Newton's second law, so balance of linear momentum or balance of the force. So by solving all of these equations all together, I can have a realistic estimate of the characteristics of the magnet. But in order to solve this equation, I need to know the properties. And the system is so large that I cannot directly go to any commercial package and then try to mesh it. That would be billions of mesh, and that would be very difficult to solve. Maybe will take several years of computation, and even then we may not have good results. So the idea is we can start to model at the micro scale for this particular, let's say, cross-sectional images, and then go on to the next scale, which is the bundle cross-section, and then go on to the full scale, which is the full MRI. And that's what I did in my PhD. So considering these microscopic images, trying to estimate the mechanical properties, we can apply stresses in different directions. As you may already know, that the stress are a tensor quantity, meaning it's different than vector and also scalar. So in order to get the properties, the elastic, thermal, the elastic and the thermal properties, we can do some form of approximation. And in addition, as I have already mentioned on this top 6, since this is a tensor, we have about 6 conditions to be applied. And for the heat capacity, this is a scalar quantity, so we have only 1 condition. And for thermal expansion, we need to apply 3 different conditions, because the thermal expansion is different in 3 different orthogonal direction, meaning the X, Y, and Z direction. And based on that, we can have an estimate of the material properties for different temperatures. As you can see that as the temperature goes, their properties are not being constant. Their properties are varying. So based on those approximation, we can include those material property that is varying with respect to temperature, and then start modeling our magnet. So the first is the winding. We can have different, let's say, boundary conditions. I mean, I can try to have the mandrel open, like not restricted by any forces or any displacement. We can also fix it in one particular direction, maybe 2 particular direction, or maybe in only from the, let's say, as actually the axial direction over here. So this is the modeling of the manufacturing process of the magnet bundle. Next, it is the cooling process. Like if I want to cool it down from room temperature down to cryogenic temperature, it is going to generate some form of thermal strains. So can we have an estimate of the thermal strain? So that's the cooling process that I can solve by using those approximated material properties. I can also solve it for electromagnetic excitations, meaning if I pass through large amount of current and then excite it to certain magnetic field, what amount of stresses and strain are being generated. So using these technique, I can combine all of those steps and processes one by one. And after winding and cool down, and electromagnetic excitation, which I, in short, specifying as charging. I can look at the entire scenario of the stresses and strain, and then check against the strain sensitivity of the magnesium diboride. Because on a smaller scale experimental study, we have figured out, or we already know, that the magnesium diboride material that I'm working on with, it can only withstand 0.4% of the tensile strain. So by no means, I cannot go beyond 0.4%. In fact, if you consider certain engineering safety factor, our limit was 0.2%. So from this analysis, we can see that the strain is about 0.06%, which is a good news. And that also means that we have some room that we can leverage the operation stage. If you remember, I discussed briefly about the quench process. So this is what it is coming next. So quench is a transient phenomena, meaning that as the time goes on, there is a change in the state variable, and we can record that. So when a quench occurs, it actually means that certain portion. So this is very difficult to identify maybe on your screen. This red spot is basically the increase in temperature. And from my simulation, we can see that the temperature has risen up to 232 Kelvin. And a corresponding strain is actually, the numbers are difficult to read here, but it's actually close to 0.07%. At that temperature. So our idea or objective is to try to understand if we can model that and take some kind of preventive measures to restrict the temperature from going beyond 200 or 300 Kelvin. And if it stays within that limit, so in addition to that 0.06%, and this is another 0.07%, then we should be able to keep the strains in the magnesium diboride within a reasonable time frame. As from this plot, as we can see, this is a temperature or time history plot. And this red plot is a quench strain without that other winding, cool down, and electromagnetic excitation. And this green is actually the electromagnetic strain. And as the time is progressing, when there are quench, the magnet is partly resistive, and we do not want the electricity to pass through at exactly the same amount. So when we detected the quench, we have some form of detection system and protection system, which eventually drains out all the electricity. And that's why this green plot is going down. And when we combine all of these and add them all together, we will have this purple line, which will give us the exact scenario or the state of the strain. So we can see that the strain does not go beyond 0.08% when we have this protection system on. So that means the magnet is being saved. And in addition to the strain in the MgB2, there were other modes of failure, which is the shear in epoxy. So there are some insulation layer, which cannot take too much of a shear. And I'm assuming that from your basic mechanical engineering or solid mechanics course, you are pretty well aware of what a shear stress or strain is. So in such scenario, we also plotted the change in the shear stress in the epoxy, and we realized that it is actually 50 megapascal that it can withstand. So if we were to use any, let's say, epoxy, we better choose an epoxy that can withstand this amount of strain. And in reality, when Ohio State, with which we were collaboratively doing this research work, they were looking for epoxy that can go beyond 150 megapascal by considering a safety factor of 3. So this was in summary of what I have done designing the MRI magnet using finite element method, and I was using ANSYS APDL for that. So I feel like I still have some time to talk about the tire research. So this was my industry research, and all of these images are from Google Images because industry research is much more proprietary. I cannot take anything out and then announce it or discuss it in the public. So the basic idea is the automotive tires that we look at from the outside is very plain, straightforward, black in color, doesn't reveal too much of an information. But if we were to cut it up and then look at its cross section, we would be able to see that there are different parts or different regions that are made out of different materials. Like there are some steel, which are metals. There are different types of polymers, which are very exciting to an engineer because they behave hyperelastically or viscoelastically, like their characteristics or constitutive behavior changes with time. There are some creep and there's some time response to it. So it's very challenging and very difficult to model. So when we, as an engineer, when we are designing a tire, we need to understand some basic concepts. So if you want to buy a good tire or an ideal tire, so ideal tire is you buy a vehicle. A vehicle usually survives about, let's say 30 years, in some cases 40 years. So an ideal tire would be a tire that is having a life that is actually equal to the vehicle life. But in reality, that does not happen. So maybe after running about 40,000 or let's say 80,000 kilometers, you would want to change your tire because it has worn out or it had destroyed or it's not capable of maintaining the pressure, inflation pressure to a level that it would require. So usually a tire has a life, like I said, 80,000 miles. So a good tire has the ability to perform under desired condition, and it is also durable, meaning it will run that number of kilometers. I'm using miles because here in US, most of the cases, mile is more, like they are more used to English unit rather than SI units. So my apology for that. But again, so in reality, the tire does not withstand that number of miles because there are some form of, let's say, damage and deformations, like some of the rubbers are coming out of it, and there might be some bulging, which is not a good thing. So how we can understand them by designing finite element modeling and then involving some form of analysis. So in finite element modeling or computational modeling, we can take a cross section made out of different materials and then do some form of, let's say, micro to mesoscale modeling. And then under some certain conditions, like let's say at what inflation pressure it is being inflated, what is the vehicle load that is coming up onto the tire, and then trying to like run some analysis at some certain conditions, like at what speed it is run, and if it is braking, then at what acceleration rate or deceleration rate it is braking. So based on those, we can have some, let's say, computational prediction of the braking distance and also the forces and moment that is being generated under certain conditions. So that's what I'm trying to show in this diagram. So we can take a cross section of the tire, model it, expand it to a 3D geometry, do some FK analysis, and then start to generate those moment versus slip angle, which is actually the driving angle or driving direction or the steering directions, and also the lateral forces. And that's what it can reveal us, and a lot of information that would otherwise not be possible by doing or running experiments. So these are a brief summary of my tire research, and I guess I have reached the end of my presentations. And at this point, if there are any questions, any open discussions, I welcome everyone to participate.
Thank you, Dr. Amin. So at this time, I open the floor to questions from the audience. If you have any question, you can unmute yourself and throw the question, or you can also use the chat box, whatever you prefer.
I have a question. Actually, I guess it was in page 7, heuristic calibration and physics guided calibration. Can you please tell me more about it?
Oh, yeah.
You compared your experimental value.
Yeah, I'm actually going to that slide. Yeah. So unfortunately, I do not have a backup slide, but I should have made it. So the heuristic calibration was some form of, let's say, heat source approximation. So when the lasers are coming up and shining on a material surface, maybe I can start to draw by using the annotation. Okay, so it's actually going onto the different direction. So let's say if I have powder bed, which is, let's say, solid surface, and the laser that is coming from the top, it is shining on top of it. Usually, if I want to numerically model it, then I just model that as some form of heat flux that is going through the surface over here. But when we try to use that as an input to our simulation, the penetration does not match with the experiment. Like it would just stay around that region. But if I'm, let's say, looking at the experiment, then it's actually much deeper, something like that. So how do we account for that change? So there are other physics that needs to be considered, but in order to make an approximation or calibration, what we did is we assume that it's basically a cylindrical heat source, like something like this. So the heuristic calibration is basically saying that if I have a laser of a given power, scan speed, and also a spot radius, that actually means that I have a volumetric heat source. Like if I will have diameter of this cylinder and also the depth of the cylinder, for which I will pick up some of the control volumes within finite volume method, and then assume that some form of heat is being generated inside those cells. And if I do that kind of heuristic calibration to model the laser, in such scenarios, I will have a good agreement with the melt pool. So that was the heuristic calibration. And the physics guided calibration is after doing some analysis and then study on my experimental data sets that are available from NIST or maybe some other literature study. What I realize is that volumetric energy density is actually linearly related with the melt pool depth and also the melt pool width. So that means that if I correlate these let's say volumetric energy density with the geometry of the melt pool, then it would have a better chance of approximating some of the predictions for the melt pool geometry. And that's what we are seeing over here. The melt pool width is agreeing pretty well once we have the physics guided calibration. So what I'm saying by physics guided calibration is it is trying to implement some form of the physics, like when the heat source that is coming from the laser would actually be representative of the heating that is happening actually in the experiment. So that is the difference. And the heuristic calibration is I'm not using a laser light that is only hitting on the surface and coming out as a surface flux, rather than I'm actually using volumetric heating. So that's what it actually means. So it's actually an approximation of the heating, not the direct amount of energy that is coming from the laser. So that's what calibration is. Is it clear to you?
Yeah, I think got it. Thank you.
Okay. And I also see there is a question in the chat box. Yeah, someone named Daud Hassan said, I have a general question. How much idea did you have about computational fluid dynamics at your undergraduate level? According to you, what would be the most effective way to learn CFD for someone with an interest? Yeah, this is a generic question. And just to share with you that during my undergrad, I was not very much familiar with CFD. And we were just learning our concepts about fluid mechanics and fluid dynamics. And from my personal experience in my BUET days, what I found challenging is we actually were not suggested a good textbook, and we struggled a lot trying to build our concept. So that was the first challenge. The second challenge was our mathematical basis or understanding is pretty limited. Again, the responsibility or let's say limitation goes back to not having a good textbook or good resources. So in order to strengthen your concept and understanding of the fundamentals of any subject, these days internet is pretty much prevalent and available. In those days when I was a student, the internet was a little bit expensive, but that was available too. So you can go search on internet trying to figure out if there are any useful sources. You can also reach out to your alumni, like senior fellows who were once studying at BUET and now at different institutes doing different types of amazing research. Reach out to them. They are very open. They're very friendly. Don't be afraid. Have a conversation with them. They would be able to guide you to better resources so that you can save lots of your effort and then build up your confidence and concept. And second part of your question, so what would be the most effective way to learn CFD? So you just stay curious. If you're curious, you would be searching on internet or maybe looking at different textbooks, and also do some hands-on stuff. Nowadays, I know you can have access to some commercial programs like ANSYS Fluent. There might be some other competitive programs like COMSOL or maybe Star CCM, or maybe you are really passionate about writing your own code. And so, yeah, you just learn C++ or Python, and then there are other, if you go to GitHub, there are lots of open source program coming from national labs, or maybe some other geek person, or maybe who really likes CFD has written some code in it. So you try to go through the code, then you will have a good understanding. And just to name some few textbook, one of our alumni who is now working for one national lab in US has recently written a book. He also gave a talk in MMMRN, I know. His name is Protono Roy. So he has recently written a fantastic book which talks about finite volume method and finite element method. You can actually read it if you want. And in addition, I can also suggest another textbook called Versteeg and Malasekara. This is one of the blue covered book and talks in details about the numerical technique of CFD. So these are very nicely written, very easy to understand. And if you spend time with it and be passionate about it, it would be very easy to understand. And even then, if you need to talk with someone, discuss with someone, reach out to your seniors who were once a student at BUET and now doing some good research work. Yeah, so just don't be afraid. Like instead of asking on chat box, why don't you just unmute yourself, unless there are some, let's say, input issues or let's say mic issues. So we are pretty open. It's like you do not need to be very afraid like we're going to criticize you for anything. So ask anything. Any other questions? Maybe not related to this presentation at all. Maybe something you want to verify, clarify.
আমি কি বাংলায় জিজ্ঞেস করতে পারি?
Yeah, sure. Yeah, হ্যাঁ, আমি তো প্রথমে বাংলায় কথা বলতে চাচ্ছিলাম, তো কে বলতেছিল যে যেহেতু রেকর্ড করা হয় ইংরেজিতে অনেকে প্রেফারেবল ফিল করে আর কি।
আচ্ছা, এডিটিভ ম্যানুফ্যাকচারিং নিয়ে কাজ করার জন্য মানে একদম বিগিনিং স্টেপটা কি হতে পারে? মানে আমি সেটা নিয়ে যদি রিসার্চ শুরু করতে চাই।
আচ্ছা, আমি ধরে নিচ্ছি যে তুমি যেহেতু বুয়েট থেকে বা বাংলাদেশ থেকে রিসার্চ করতে চাও, তার মানে তোমার এক্সপেরিমেন্টাল ফ্যাসিলিটি হয়তো লিমিটেড, মানে এক্সপেরিমেন্টাল কাজ করার স্কোপ হয়তো তোমার অনেক লিমিটেড। সো ওই সেন্সে তুমি যেটা করতে পারো, কিছু কমার্শিয়াল সফটওয়্যার অথবা ওপেন সোর্স সফটওয়্যার ওইগুলো তুমি দেখতে পারো তুমি রান করতে পারো কিনা। মানে ওগুলো যদি তুমি ঠিক মতো শিখতে পারো, তখন তুমি যেটা করতে পারো যে লিটারেচারে দেখতে পারো যে মানুষজন কি কি ধরনের এক্সপেরিমেন্টাল কাজ করেছে, সেটার উপর বেস করে তুমি হয়তো ওগুলো প্রেডিকশন করার মতো চেষ্টা করতে পারো। আমি জানি তোমাদের এখানে বেশ একটা স্ট্রং কমিউনিটি আছে যারা তোমার মলিকুলার সিমুলেশন নিয়ে কাজ করো, ঠিক আছে? সো এই অ্যাডিটিভ ম্যানুফ্যাকচারিংটা অনেকটা সিমিলার, মানে তুমি এমন অনেক প্রোগ্রাম পাবে যেগুলো অ্যাডিটিভ ম্যানুফ্যাকচারিং এর প্রবলেম সলভ করছে। জাস্ট তোমাকে প্রবলেমটা খুঁজে বের করতে হবে যে মানুষজন যেটা আগে সলভ করতে পারে নাই। তো এটার জন্য তুমি যে গুগল স্কলারে গিয়ে রিসার্চ আর্টিকেল পড়ে দেখতে পারো। অনেক সময় ধরো অনেকে তোমরা মাস্টার্স সরি আন্ডারগ্রেড থিসিস যখন শুরু করো 4th ইয়ারে, হয়তো ওইদিকে অ্যালাইন করে যদি তুমি মানে প্রপোজাল দিতে পারো তোমার রেসপেক্টেড ফ্যাকাল্টি অ্যাডভাইজারের কাছে, ওনার যদি পছন্দ হয় তাহলে তোমার এফোর্টটা কমে গেল। মানে তখন যেটা হবে যে তুমি হয়তো ফ্যাকাল্টির কাছ থেকেও হেল্প পাবা, বা সিনিয়র ভাইয়ারা বা আপুরা যারা আছেন তাদের কাছ থেকেও হয়তো হেল্প পাবা। আর আমি পার্সোনালি বলতে পারি যে আমার স্ট্রেংথ হচ্ছে তোমার কোড ডেভেলপমেন্ট, বা মনে করো ওপেন সোর্স কোড ডেভেলপমেন্ট বা সি প্লাস প্লাস প্রোগ্রাম রাইটিং, এগুলো। সো যদি কারো ইন্টারেস্ট থেকে থাকে আমরা কথা বলতে পারি বা আমরা একসাথে কাজ করতে পারি। জাস্ট আমার যেহেতু কিছু এক্সপিরিয়েন্স আছে অ্যাডিটিভ ম্যানুফ্যাকচারিং এ, সো যদি ইনিশিয়াল ডিরেকশন দরকার হয় আমরা কথা বলতে পারি বা একসাথে কাজ করতে পারি। কোনো ফলো আপ কোয়েশ্চেন বা অন্য কোনো কোয়েশ্চেন কারোর কাছ থেকে? আচ্ছা, আমি তোমাদের জন্য জেনারেল একটা কোয়েশ্চেন করি। তোমরা কোন ব্যাচ বেসিক্যালি, মানে সবচেয়ে জুনিয়র কে আর সবচেয়ে সিনিয়র কে? এখানে অবশ্যই এখানেও তো আমি সিনিয়র, আমি 03 ব্যাচ। তো তোমাদের সবচেয়ে জুনিয়র কে?
মানে বুয়েটে এখন সবচেয়ে জুনিয়র 21 ব্যাচ।
আচ্ছা, কিন্তু এখানে আজকে যারা প্রেজেন্ট আছে তাদের মধ্যে সবচেয়ে জুনিয়র কে?
পার্টিসিপেন্ট লিস্ট আই গেস ভাই
Miss-
18 ব্যাচ হতে পারে।
আচ্ছা আচ্ছা, আর তোমাদের মধ্যে সবচেয়ে সিনিয়র মানে এক্সেপ্ট মি?
17 ব্যাচ।
আচ্ছা, ভালো। তাহলে তোমরা 18 ব্যাচ, তাহলে এখন কি লেভেল 3 তে?
হ্যাঁ, ওরা লেভেল 3 টার্ম 2 তে।
আচ্ছা, আর তোমরা অলমোস্ট গ্রাজুয়েট করতেছো যারা 17।
হ্যাঁ, আমাদের আর 5 উইকস এর মতো আছে।
আচ্ছা, তো 5x এর মতো যদি হয়, আচ্ছা একজন বলছে হচ্ছে he is not from Buet, but anyway, so yeah, Daud Hassan, I think you can unmute yourself and we can have a discussion. So it's nothing against someone not being from Buet. Buet থেকে কেউ না হলে আমরা তাকে ক্রিটিসাইজ করছি এমন না। তো তুমি যদি আনমিউট করে তোমাকে একটু মানে ইন্ট্রোডিউস করো তাহলে বেশ ভালো হয়। তুমি কোথা থেকে, বা তুমি আসলে বাংলা বলতে পারো কিনা?
সালাম আলাইকুম।
ওয়ালাইকুম আসসালাম।
ভাইয়া, আমি দিনাজপুরের হাজী মোহাম্মদ দানেশ বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের মেকানিক্যাল ইঞ্জিনিয়ারিং ডিপার্টমেন্টে পড়তেছি।
আচ্ছা, শুনে খুব ভালো লাগলো। সো
আমার আমার বাসা চিটাগং, আর
আচ্ছা
দিনাজপুরে এখন থাকতেছি। জি। আর
আচ্ছা,
মূলত আমাদের ইউনিভার্সিটির যে টিচার, ওনারা
হুম,
তো বুয়েটের আন্ডারগ্রেড করা, তো ওই দিক থেকে এই ট্রিপল এমআরএন এর সাথে সংযুক্ত হওয়া আর কি।
আচ্ছা। তো আমি আশা করবো তুমি হয়তো মানুষজনের সাথে আর ইন্টারঅ্যাক্ট করবে, এবং MMMRN আসলে বেশ ভালো একটা গ্রুপ, মানুষজন সবাই খুব হেল্পফুল। তোমার যদি কখনো কোনো সাহায্য দরকার থাকে তুমি পোস্ট করতে পারো গ্রুপে, বা অন্য যারা অ্যাক্টিভ আছে তাদের সাথে ইন্টারঅ্যাক্ট করলে আশা করি তোমার যে কোনো সমস্যার সমাধান হবে।
জি ভাইয়া, থ্যাংক ইউ।
আচ্ছা আচ্ছা, আর কোনো কোয়েশ্চেন? নাথিং রিলেটেড টু প্রেজেন্টেশন, মেবি হায়ার স্টাডিজ? তোমরা যেহেতু গ্রাজুয়েট করে যাচ্ছ, আশা করতেছে হয়তো কেউ অ্যাপ্লাই করছো ফল 23 এর জন্য।
ভাই অ্যাকচুয়ালি মানে হায়ার স্টাডিজ নিয়ে কোশ্চেন তো মানে সামনে তো হচ্ছে আমরা মানে এটাকে পদার্পণ করতে যাচ্ছি আর কি।
হুম,
আহ,
হুম,
তো অ্যাকচুয়ালি অ্যাডিটিভ ম্যানুফ্যাকচারিং ফিল্ডে মানে হচ্ছে মানে ওই ফিল্ডের ইয়ে কেমন, যেমন লাইক আমি আমি এমএমএমআর এর সাথে যুক্ত, তো আমি ইয়েতে কাজ করি,
হুম,
আমি
হুম,
ল্যাম্পস দিয়ে আমি ন্যানো মেকানিক্সে আপাতত কাজ করতেছি। তো
হুম, হুম।
অ্যাকচুয়ালি অ্যাডিটিভ ম্যানুফ্যাকচারিং ফিল্ডটা নিয়ে আমার একটু ইন্টারেস্ট আছে। তো মানে এটা
আচ্ছা,
নিয়ে যদি একটু স্কোপস এন্ড
হুম। এটা রিসেন্ট টাইমস হচ্ছে আহ, বেশ ভালো ফোকাস। তো তুমি যদি রিসার্চ করতে যাও এটাতে বেশ ভালো অপরচুনিটি আছে, কারণ তোমার অনেক ফ্যাকাল্টি আছে যারা অ্যাডিটিভ ম্যানুফ্যাকচারিং এ রিসার্চ করে বেসিক্যালি। তো মানে ইন টার্মস অফ গ্র্যান্ট বা ফান্ডিং যদি বলো, হয়তো আহ, হয়তো একটু বেটার, বা অথবা তোমার কম্পিটিটিভ মানে অন্যান্য এরিয়ার তুলনায়। সো তোমার যদি ইন্টারেস্ট থাকে তাহলে তুমি আরো জানার চেষ্টা করতে পারো, আরো মানে পেপার পড়ার চেষ্টা করতে পারো, সেটার উপর বেস করে হচ্ছে তুমি বিয়ে করতে পারো, মানে নিজের ডেভেলপমেন্ট হতে পারে মডেলিং। আর আমি আশা করছি বাংলাদেশে মনে হয় আসলে এক্সপেরিমেন্টাল ফ্যাসিলিটি নাই। বুয়েটে বা অন্য কোনো হাজী দানেশ ইউনিভার্সিটিতে কি কোনো অ্যাডিটিভ ম্যানুফ্যাকচারিং ফ্যাসিলিটিস আছে, মানে তোমাদের জানা আছে?
না ভাইয়া।
আচ্ছা, হ্যাঁ, আচ্ছা, তাহলে তুমি যেটা মানে বেস্ট তোমরা যেটা করতে পারো হয়তো কম্পিটিশনাল কাজ করতে পারো। সো এটা তোমার মোস্টলি যে ফাইনাইট ভলিউম অ্যাক্সিস ফ্লুয়েন্ট বা ফ্লো 3D যদি নাম শুনে থাকো এটা একটা, অথবা হচ্ছে তোমার ওপেন ফোম, তোমরা নাম জানো কিনা? ওপেন ফোম একটা হচ্ছে ওপেন সোর্স সলভার, সিএফডি সলভার টু সাম এক্সটেন্ট। ওইটা দিয়েও তোমরা সিমুলেশনের কাজ করতে পারো, এবং সেখান থেকে হয়তো আইডি ম্যানুফ্যাকচারিং এর রিসার্চ আগে নিতে পারো।
জি ভাই, থ্যাংক ইউ।
ওকে, সো আর যদি কোনো কোশ্চেন না থাকে তাহলে আমরা কি এন্ড করব সুন? Okay, if not, then thank you for inviting me. Thank you for listening to my talk. And again, if there are any questions, you can basically, let's see, I can jump onto my slide number 29, I guess, where my contact information is. You can send me an email if you feel like. Let me clear some stuff, and I guess that would be much easier. Oh, no, not that one. Yeah, so that's where my information is about. And I can also write it on the chat box. Yep, so do reach out to me if you have questions. If not, then thank you again for joining, and hopefully see you in some form or some way at some time in the future.
Thank you, bhai.
থ্যাংক ইউ,
Okay, thank you. Bye.
থ্যাংক ইউ।